Good morning. So, this is the course on engineering thermodynamics. The lectures and example problems have been covered by Professor V. Babu, Department of Mechanical Engineering, IIT Madras. So, I am Professor Raghavan of the same department from IIT Madras. Now, we will discuss about the tutorial problems. The first tutorial is on basic concepts. The first problem is the variable phi depends on temperature and volume. The change in the value of phi is written as AT square plus BT plus C times dt plus RT by V into dV. So, we need to find whether phi is a property or not. So, phi depends on, so a change in phi can be written as the change of the function with respect to the temperature when volume is constant into dt plus dou f by dou v, the change of function with respect to the volume when t is constant into dv. Now, this I call m and this I call n. So, t phi will be equal to m into dt plus n into dv. Now, if d phi is an exact differential, that is a property. So, we know that a property has to be an exact differential. If d phi is an exact differential, then this should obey the condition dou m by dou v equal to dou n by dou t. If this is satisfied, then we can say that d phi is an exact differential. Now, what is dou m by dou v? Here you can see that m equal to a t square plus b t plus c. There is no v here, so this is equal to 0. Now, what is n? n equal to r t by v. Now, dou n divided by dou t will be equal to r by v. So, now we see that dou m by dou v is not equal to dou n by dou t. So, this means d phi is not an exact differential or phi is not a property. Okay, so this is the fundamental rule of the mathematics which we use to determine whether phi is a property given the change is represented by this equation. On the other hand, if you consider a function where say this is a t square plus b t plus c times dt plus let us just have r by v into dv, then this, if this equal to d phi, then we can say phi is a property. Then we can say that because you can see that here m will be this same as previous. So, dou m by dou v equal to 0. Now, similarly n will be only r by v. So, dou n by dou t will also be equal to 0. So, this is a property. So, this relationship is a property, but this is not. Now, second problem, discuss the path independence. So, you know that properties are path independent. That is, if I have, see, this is basically a state diagram. Now I have 4 points here A, B, C, D, and the y axis is P, x axis is V, and you can see that A 1, 2 means the volume is 1 meter cube and P is 2 bar. Similarly, D volume is 1 meter cube, P is 3 bar, and so on. So, these are all state points. A, B, C, D are state points. Now, property, if we say what is change in the property between A and C for P. So, dP between A and C, I can say it is 3 minus 2, that is 1 bar. So, that means if I reach A to C through D or through B, that does not make any difference. Only the final state and initial states are important. Now, I want to see whether these integrals are path independent or not. I have 3 paths. Now, one path is A to B, B to C, A, B, C. Second path is A to B to C, that is A, D, C. The third one is directly from A to C. So, these 3 paths. So, if I integrate this P dV from A to C, so the initial state is A, final state is C. Okay, so this is the initial state and this is the final state. But the path used to reach C from A is different. It may be A, B, C, it may be A, D, C, or it may be directly from A to C. So, if I integrate this P dV in these 3 paths and see whether the answer is same in all these 3 integrals, then we can say it is path independent. So, let us do this. So, we will take this. So, integral A to C to the path A, B, C, P dV will be equal to integral A to B P dV plus integral B to C P dV. So, now I can easily do this P dV A B. So, here P is 2 bar, here also P is 2 bar. So, 2 is constant, I take it out. V varies from 1 meter cube to 2 meter cube. So, 2 minus 1. So, it is 2 bar meter cube. Okay. So, something like that I can write, or it can say this as 200 kilojoules, because 1 bar equal to 100 kilojoules, kilopascals. 1 bar equal to 100 kilopascals. So, I can say 2 bar meter cube will be equal to 200 kilopascals meter cube. So, this is 200 kilojoules. Now, I will do the same integral A to C. Now, I will use the path ADC. P dV will be equal to A to D P dV plus D to C P dV. 2 paths. Now, what is A to D? A to D is a constant volume process, because volume remains at 1 meter cube, pressure increases. So, that means 0, because dV is 0. So, integral P dV A to D is 0. But if you take D to C, it is what? D pressure is 3 bar and C also pressure is 3 bar. So, plus 3 into constant pressure, change in volume is again 2 minus 1. So, here it is 3 bar meter cube equal to 300 kilojoules. So, now itself you can see that when you go for the integral from A, B, C, it is giving value of 200 kilojoules. If it is through A, D, C, it is giving 300 kilojoules. That means this is already path dependent. Obviously, A to C also you can do and see. What happens here is there is a pressure variation from 2 bar to 3 bar, but it is linear. So, average pressure in this will be 2 plus 3 by 2, that is 2.5 bar. So, I can say 2.5 into 2 minus 1, that is 2.5 bar meter cube or 250 kilojoules. So, we can see that all the 3 parts gives 3 results here. That means this is this integral obviously, which is nothing but displacement work. Displacement work is path dependent. Integral PdV is path dependent. So, we cannot, so that is not a property. Now, let us take the last example. You can work it out and see this VdP. Obviously, this will also be path dependent. Let us do this. Integral, that is third one, is integral A to C P dV plus V dP. So, which is equal to integral P of PV d of PV A to C, correct, because dP d of PV will be equal to P dV plus V dP, chain rule. So, now in the path, so let us do this. In the path ABC, d of PV will be equal to integral A to B d of PV plus integral B to C d of PV. So, which is equal to what? Here PV B minus PV A plus here PV C minus PV B. So, you can do this and see that it is PV of C minus A, because this cancels. So, it will be PV of C minus PV of A, which clearly says that integral A to C dPV ABC is equal to integral A to C through A C directly dPV. These are equal because I am only getting this. So, just verify the ADC now. So, integral A to C dPV in the path ADC will be equal to integral A to D of dPV plus integral D to C of dPV. So, here also you can see that it is PV here D minus PV A plus PV C minus PV D. Now, you can also see this PV A minus PV C minus PV A results, which is same as this. That means you will have this, the third is path independent. 1 and 2 are path dependent. So, this is an example of verifying whether a particular integral, because you can see this dPV itself is a change in a property. The property is PV, that is it. So, for example, enthalpy is U plus PV, it is a combination of properties. This is also a combination of properties. So, this should be a path independent integration. Now, third problem, a cylinder with total volume of 1 meter cube. This cylinder A plus B together as a volume of 1 meter cube is as a movable piston as shown here. The piston is at 1/4 of the length. Both sides have same specific volume. So, here total length is L. When the piston is located at L by 4 from the left side, then the chamber A and chamber B has some gases or some material. The specific volume is same, which is equal to 4 meter cube per kg. Now, determine the specific volumes of both the sides if the piston is at the middle. Instead of at L by 4, if the piston goes to middle, I am drawing in a dotted line. So, if it is in the middle, this is L by 2, what will be the specific volumes? So, that is the problem here. Here solution. So, 1 meter cube is the total volume, say V equal to 1 meter cube. So, when piston is at L by 4 from left, VA equal to what? V equal to 0.25 meter cube and VB will be equal to 0.75 meter cube. So, specific volumes are same here for this case, that is mass in A will be equal to what? Total volume in meter cube in A divided by the specific volume in meter cube per kg. Okay. Now, this what is this? This is 0.25 divided by 4 kg. This is equal to 0.0625 kg. Similarly, mass in the chamber B is what? Mass in the chamber B is total volume of B in meter cube divided by the specific volume of B in meter cube per kg, which is equal to what is total volume? 0.75 divided by the specific volume is same in this particular condition. So, it is 0.1875 kg. So, now the masses are got. So, now when the piston is in the middle, then what happens? VA is equal to VB equal to 1 by 2 equal to 0.5 meter cube. So, the volume is determined. Mass is also known. So, now find specific volumes. So, VA equal to what? VA equal to VA, the total volume of the chamber A divided by the mass in the chamber A, which I know now, 0.5 divided by 0.0625, which is equal to similarly, this is 8 meter cube per kg. Similarly, VB equal to 0.5 total volume divided by 0.1875, 2.6667 meter cube per kg. So, you can see that depending upon the mass and the volume, the specific volume will change. Okay, density. So, if rho is the density, density will be equal to 1 by specific volume. Okay, so that is the another example on properties. Now, go to the next one. A cylinder with a volume of 10 meter cube contains 5 kg of oxygen. So, what is the density of the oxygen? Density of oxygen will be equal to mass per volume, which is equal to 5 by 10, 5 kg per 10 meter cube. Okay, now next, during certain process 3 kg of oxygen is consumed. What is the density of the oxygen in the cylinder? So, when 3 kg is consumed, that is extracted from the cylinder. Three kg is extracted from the cylinder, then remaining mass is but the cylinder, the volume will not change. So, volume of the cylinder is 10 meter cube. That will not change. So now density will be equal to 2 by 10 equal to 0.2. So it's a cylinder is a rigid volume made of metal, and you can extract the oxygen from this. Once oxygen goes out, the density of the oxygen in the cylinder will decrease obviously, because it is mass per unit volume. On the other hand, if you have specific volumes, let us do specific volumes also. Volume when mass is 5 kgs. What will be specific volume? It will be VO2 at 1, I will say 5 kgs will be reverse of this. This 2 meter cube per kg. And when mass is 2 kgs, then specific volume will be equal to 10 by 2 equal to 5 meter cube per kg. So you can see that increase in the specific volume occurs when the mass decreases. Okay, so it's the inverse. So now fifth problem. Consider a horizontal tube 1 meter long, sealed at both ends. So this tube is 1 meter long, sealed at both ends. The middle 10 centimeter of the tube contains mercury. So something like this. It contains mercury. Contains mercury, and the rest of the tube contains air. So this is air. This is also air at atmospheric pressure. So here the pressure is P atm here and also here. So atmospheric pressure also is given as 76 centimeters of mercury. That is rho mercury into G, the acceleration due to gravity, into H. That will be the H is 70 centimeters. So this is the pressure atmosphere. So here you can calculate this as 13,600 kg per meter cube into 9.81 meter. So due to gravity, acceleration due to gravity, so 9.8 meter per second square into H is 76 centimeters, that is 0.76 meters. So that will be the atmospheric pressure. So when atmospheric pressure can be given in terms of height of water column or height of mercury, etc. So here when it is given, then the pressure in pascals, this is the pressure in pascals, can be found by using this rho GH. The what will be the, see, if it is mercury, density of mercury should be used. If it is water, water's density should be used, and whatever will be the height. Okay, now this is the scenario. Now what is this? This is 10 centimeters. It is given 10 centimeters. So now that means this will be totally 1 meter, that is 100 centimeters. So now 10 centimeters is gone. So here it will be 45 centimeters. So 45 plus here 45, 90 plus 10, this 10. So totally 1 meter. So this is the arrangement. Initially the tube is now brought to vertical position. Instead of this, just it is tilted to the left or right side, so that it becomes vertical position. So I can draw this here. So what happens? The mercury will now, the mercury is initially in the middle, no, this is like this. Mercury will start descending down because of its weight, it will start to come down. So let us say that the mercury has, I will first erase this, and mercury has come down to this level somewhere here, and it stops because air is there. It is going to compress this air. So both sides initially has air. So here it will come down and basically compress this air. Okay, so how much distance it will fall? That's what it is asking. So let mercury fall by h, you can see in centimeters, h centimeter. So that means now I can draw the heights here. This will be what? 45 plus h centimeters, and this is mercury will not deform because it's very huge density. It will not deform. So this will remain as 10 centimeters. Now the bottom, the height would have reduced to 45 minus h centimeter. So this is centimeter. This. So what is h? I want to calculate what is h. That's it. Okay. Now further it is given that assume that changes in pressure and volume for the air, because air, the pressure is changing. Initially air is at atmospheric pressure. Now when the mercury compresses the air, this particular part, so let us say this is bottom part and this is top part. Top part you have increase in volume, bottom part decrease in volume. So pressure and volume changes, but it obeys because it is like isothermal, there is no temperature change. So and if air is ideal gas, then PV equal to RT, MRT. So but temperature is constant, mass is constant, and specific gas constant is also constant. So we can say PV equal to constant. So this relation is obeyed. Okay. So now how to calculate H? Okay. Now what we will say is the initial volume V, initial volume will be what? Area of cross section of the tube, whatever it may be, A into length is 45 centimeters. So 45 into 10 power minus 2 meter. Area is in meter square. And this is this. So this is the total volume in meter cube. Now h is the distance descended by the mercury. That means when I say Pt is the pressure at top part and Pb is the pressure at bottom part. Okay, now I can write, since PV equal to constant, I can write what? P atmosphere. First initial condition, pressure is atmospheric pressure in the both air columns. Now after making it vertical, the pressure would have changed. So initially this will be this into pressure P atmosphere into A into 45 into 10 power minus 2, that will be PV. That will be equal to, say, top part Pt into A into, now top part 45 plus h is the height of the column now into 10 power minus 2. Okay. So now we can easily see that from this Pt can be written as 45 into P atmosphere. So I know what is how to calculate P atmosphere. Here I have given the expression. So P atmosphere divided by 45 plus h. Do you understand? So now P atmosphere I know I have to calculate by rho GH. So rho GH I can substitute here. So this is the expression. Now for the bottom part, what happens? Pb. So Pb here pressure is what? Whatever be the pressure at the top, Pt plus, now mercury also is going to impart pressure. So that is density of the mercury H rho Hg into the acceleration due to gravity into what is the length 10 into 10 power minus 2. So this will be the pressure. So I know what is the expression for Pt I know, and rho rho Hg g into 10 minus 2, that also you know. So further I have the expression P atmosphere into 45 into A into 45 into 10 power minus 2 equal to Pb. This also is obeyed, correct? So Pb into A into 45 minus H into 10 power minus 2. So this is the expression I have. So now I can substitute for Pb here in this. This is expression for Pb. I can substitute here and get an expression. So now when I do that, I get a quadratic equation in X. If I substitute and simplify, I get a quadratic expression 0.1 H square plus 68.4 H minus 202.5 equal to 0. So this is the expression I get when I substitute this. So now the positive solution for this is H equal to 2.94 centimeter. That is the answer. So when I tilt this horizontal arrangement to vertical arrangement, the mercury falls by around 3 centimeters. So that is the answer. Okay. So this problem you can see that the variation of the air obeys PV equal to constant because temperature is constant here.